Good evening, everyone. It is our last Wednesday Speakers Night for 2022. I am very happy to be here with you tonight. We have all kinds of amazing stuff planned, but um, as a way getting started here, let me just go ahead and say welcome back to the RASC Toronto Centre. We are on the line tonight, journeying to the winter solstice, and as I mentioned before, having our very last Speakers Night of the year. I'm Dr. Elena Hyde, the second vice president of the RASC Toronto Centre, and this is our November 2022 Speakers Night presentation. This is one of two types of gatherings that we have online these days, not at the Ontario Science Centre due to the pandemic. And later on this evening, our president, Tom Luton, will be talking about all kinds of various programs. But first, we have a very special event to kick off. So, to get us started here tonight, I would like to just take a minute of your time to acknowledge that the Royal Astronomical Society of Canada Toronto Centre meets on the traditional territories of many Indigenous nations, including the Haudenosaunee Confederacy, the Huron-Wendat, the Mississaugas of the Credit First Nation, and other Anishinaabe peoples. These lands are part of the Dish with One Spoon Treaty and are now home to many diverse First Nations, Inuit, Métis, and Indigenous peoples from across Turtle Island. As we engage in astronomy here tonight, together, we respect, learn from, and honor the deep relationship between Indigenous peoples, the sky, and the earth. Now, as I mentioned before, this is an extra sort of exciting event because, of course, this is our last Speakers Night of the year. And this year has been quite a doozy for astronomy. We've had lunar eclipses, two of them by my count, numerous astronomical events, and recently even a launch of the Artemis 1 program. So tonight we're continuing the astronomy awesomeness with our speaker, Ismaël Moumen. So just to go ahead and give them a little bit of an introduction, if you haven't heard of them before, well, you're in for a treat. Ismaël is a final year PhD student at Université Laval and the Canada France Hawaii Telescope. His research it focuses on quite a bit, few different things, but in particular, some of the physics around H2 regions and supernova remnants in nearby galaxies using 3D spectroscopy, which I'm sure he will tell us about tonight. So I'll leave that to him. He is also involved in a couple really interesting socio-scientific projects aiming to democratize access to astronomy and using it as a tool for societal development. Ismail is, in fact, the leader of the Astronomy in Indigenous Communities, or AIC project, that aims to collaborate with Indigenous communities to provide students with opportunities to explore the night sky and the universe from both indigenous and Western perspectives. And if that wasn't enough, he's also the co founder and executive director of the Arab Astronomical Society, aiming at developing astronomy in the Middle East and North Africa. So, always really fun to hear these talks, and I cannot wait to hear this one. So, our speaker has quite the show lined up. So, let me go ahead and say, Ismail, please take it and us up, up, and away.
Yeah, good evening, everyone. Thank you so much, Elena. Thank you to the RASC for your invitation. So you did a great presentation. So I'm today here to present observation of galaxies in the new era of 3D spectroscopy. So just a quick presentation. Elena did the perfect presentation for me, better than me. So I'm final year student, PhD student in astrophysics. I'm studying star formation regions, H2 regions, and supernova remnants in nearby galaxies using 3D spectroscopic data. I'm using CTEL data from Canada France Hawaii Telescope. Yeah, so I'm PhD student at Canada France Hawaii Telescope and University Laval. I'm also working at the government of Canada as a research assistant. And next winter, I will start a job like instructor of astronomy course at the Wilfrid Laurier University. And also for outreach, I am very excited and I like so much to be involved in the society. So I'm leading some projects. Two of them, two main projects are the astronomy in indigenous communities. We use astronomy as a tool of development for indigenous students, and I am also co-founder and executive director of the Arab Astronomical Society. So we organize in schools, conferences, and workshops for students in the North Africa and Middle East. So 22 countries speaking Arab language. But today I'm here to talk about science, and to do that, I will go back in the past. I will go back almost 100 years ago, and to remember the great debate. So exactly in April 26, 1920, at the Smithsonian Museum of Natural History, two big astronomers, Harlow Shapley and Heber Curtis, meet there to discuss the nature of some objects identified as a spiral nebula, and also to discuss our place in the universe. I like to describe that like, are we alone in term of in term of galaxies at this time? Because at this time, Shapley suggested that we have only one galaxy. Our galaxy is a very big galaxy. There is no other galaxies in the universe. We are the universe. We are the big galaxy. In the other side, Curtis suggested that the spiral nebula that we identified at this time are also galaxies like the Milky Way. So we are galaxy among uh, billions of galaxies in the universe, and what we are observing at this time were other galaxies like ours. So yeah, so for this great debate in Shapley's model also, he put the sun far from the center. However, Curtis put the sun near of the center of a small galaxy. But later, using observation of galaxies and thanks to Edwin Hubble was able to identify Cepheid variable stars in the galaxy M31 in the Andromeda galaxy. So he uses his telescope to identify these Cepheid stars, and he was able to estimate the distance. And he found that the distance of M31 Andromeda galaxy was higher than what Shapley found in his model. So that means that this object, this spiral nebula, is located outside our galaxy, which means this is another galaxy, and then there are a lot of other galaxies like our galaxy in the universe. So further observation in 1926 came and confirmed this theory. So we are not alone. There are a lot of galaxies in the universe, and billions of galaxies in the universe. So the most important messenger to speak with us to describe these galaxies, the formation and the evolution of these galaxies is light. That's why I want also to talk about light, because light coming from nearby galaxies and also from faraway galaxies give us a lot of information about the physical and chemical and also kinematic characteristics of this object, which help us to build scenario of formation and evolution. So to talk about light, we remember a few years ago, exactly in 2015, humanity commemorated the International Year of Light. So a lot of events everywhere in the world were organized to talk about the history of the light, the different contributor that describe the light and that played important role to understand the physics of light. So one of them, and it is not very known, was Ibn al-Haytham. So Ibn al-Haytham was born in Iraq and died in Cairo, and he published a very important book, a very important reference. This book, the name is in Arabic, Kitab al-Manazir, so the book of optics, and it was a big reference, I think 6 or 7 books talking about his own theory of light. So during this year, so why they choose 2015? One of the reasons was the 1000th anniversary of the publication of this book, Kitab al-Manajis. So there are lots of events in the world, in Asia, Europe, and everywhere in the world to talk about these scientists that a lot of people that don't know, and he is a great and known scientist. So I will leave you with the video talking about Ibn al-Haytham.
If learning the truth is the scientist's goal, then he must make himself the enemy of all that he reads. In the words of Isaac Newton, if I have seen further, it is because I stand on the shoulders of giants. I wonder who those giants were. The quest of every true scientist to truly understand our world.
So, if you want to know more about this scientist, they have created a website. Is www.ibnulhaytham.com, describing his publication and his works related to the light. And he developed his works when he was in the prison. So later, Isaac Newton came to present one of the first theories for light. So, in his model, he suggested that the propagation of light was caused by rectilinear motion of light particle. So, for him, and he gave for that the name of light corpuscles. So, for Isaac Newton, light was a particle, and the light particle was traveling at a finite speed, and these particles were able to interact with the matter following Newtonian physics. So after that, in 1801, the scientist Young began a series of experiments related to the phenomena of interference. So he observed that when the light go inside the slit, there is creation of two beams of light, and when they are recombined, there are presence of interference. So we have fringes, dark and light fringes, which means they can be constructive or destructive, which means that light for him was a wave. After that, in 1839, the experience of the photoelectric effect came to give another nature of the light. So, when light shone onto a metal surface, it causes the ejection of electrons from this metal. Uh, so it was observed that the energy absorbed respected certain frequencies. So it was quantified. And thanks to the photoelectric effect, the light now have the nature of wave and particle. So the light is a wave and a particle at the same time. In 1864, James Maxwell gave the first complete theory of light by presenting his equations of light, and he proposed that light in the same medium causes the electric and magnetic field that are interacting to produce light. So quickly, the some main characteristic of light. One of the main characteristic is the wavelength. So the distance between the top of the wavelength to the other top, and we can have short wavelength and long wavelength. And the wavelength is the inverse of frequency. So when we have short wavelength, we have a high frequency, and the same thing for long wavelength, we have low frequency. And Planck found a relation linking the energy of the light with the frequency of this light, and he introduced the Planck constant. So we can obtain the energy of the light if we know the wavelength or the frequency of this light. Also, what we can find is the temperature of the object. So using Vein law, we are able to find the temperature of the light if we know the peak of this body. Also, uh, we can mini works of Steven Boltzmann and Steven and Boltzmann. So we have two equations to estimate the surface brightness of the object and the global luminosity, which are both of them related to the temperature of the light power 4. So using characteristic of light, we can have different information of the objects, the energy, the surface brightness, the luminosity, and the temperature. So now we will talk about spectroscopy. And to do that, I want to ask you if you are if you are here. Okay. Who has ever seen a spectrum of light? So if not, who has ever observed a rainbow? Because a rainbow is a wonderful example of a spectrum. say it slow. It's time. Sorry. Okay, it's coming. Yeah, so the rainbow is a wonderful example of a spectra of a spectrum. It's only one part of the electromagnetic spectrum. So spectroscopy is the study of absorption and emission light from of other radiation from by the matter, and it consists of splitting the light on different wavelength and intensities. So what we have access, human, we have access only in a small part of the electromagnetic spectrum, the optical part. So there are lot of windows, spectral windows that we don't have access from the radio to the gamma ray. And in astronomy, astronomers use the entire electromagnetic spectrum to observe and study a variety of astrophysical objects. So from radio waves and microwaves, uh, they have the longest wavelength, so the lowest energy. They can study objects with low energy, and at the inverse, they can study objects with high energy, like supernova and AGN, etc., using gamma ray and X-ray. And we human, we have access to this small part of the visible window. So there are three types of spectra: continuous spectrum, emission spectrum, and absorption spectrum. The first one, the continuous spectrum, is produced by a hot and object. Normally, it's a black body. The absorption spectrum is produced by a cold or cool gas. So we have absorption lines here, dark lines in the continuum spectrum, and the last category is emission spectrum when we have a hot gas. So we can have emission lines in this spectrum. And here I present example of a spectrum in graph format. So when astronomers study the spectra of objects, normally they have like absorption spectra like this, and emission spectra like this one. We have emission lines here and absorption lines here. And this is a good example of emission, is in particular emission line spectrum. So we have different emission lines, H alpha, H beta, O3, and different chemical elements having emission lines. We have also some absorption future, but for each two regions, star forming regions, we have stars inside a gas, and the stars are very hot. They input a lot of energy to the gas, so we have hot gas producing emission lines like this. And now and recently, we have the introduction of the 3D spectroscopy. So the 3D spectroscopy, or the integral field unit, is combine the imaging and the spectroscopic capabilities. What is wonderful in this technique, we have access to the spectral and the spatial information at the same time. So in the past, we have only access to one single pixel or few pixels in objects, so we can't cover all the extended objects. But with the 3D spectroscopy, we have information for each pixel of the object, and we have spectrum for each pixel. So it's provide wonderful data set to study different physical and chemical characteristics of extended objects like galaxies, in particular nearby galaxies, emission nebula like supernova remnants, H2 regions, planetary nebula, and also crowded stellar fields. And there are different type of or different techniques of 3D spectroscopy. The first one is lancelet. In this type of IFU, the lancelet array is placed in the spectrograph entrance and slits the plane, and it is acting like a spatial pixel or a spectrum. So we have each part of the object in the focal plane. We have a small slit, and for each split we have a spectrum for this part. And after that, we do recombination to recreate the data cube of the original objects, and with having a spectra for each part of the spectrograph. The second example is fibers, and in this case, the light of the target are captured by an array of fiber, like we can see here, and single slits for each fiber is connected for each fiber to give spectrum for this fiber. So we have different fibers here, and each fiber we have slits, and each slits give us a spectrum. And also here the combination of the spectrum, we create a data cube having spatial information and spectral information in the third dimension. And the last example is image slicer. So in this example, we have the image is sliced on different slices, and we arrange the spectrograph input to cover each part of the image slice, and we have a spectrum for each. We have spectrum for each slice in this image. And again, we have to do reproduction of the data cube to have the spatial and the spectral information. Some examples of these instruments are SORON at the William Herschel telescope for lenslet spectrograph, and for fibers, we have lots of examples like Integral at the William Herschel telescopes, Khalifa, a very famous survey using this kind of instruments at the Caltar Alto Observatory. We have SAMI at the Australian Astronomical Observatory, and the MANGA, which is one of the surveys making up the next generation of the SDSS. And for the image slicer, we have a wonderful example is Muse at the VLT. But today I want to talk to another technique for 3D spectroscopy is the Fourier transform spectrograph using Fourier transform spectroscopy. So this technique uses the interferences of light rather than dispersion. So when we use this technique, we don't have directly a spectrum. What we obtain is the interferogram that we apply Fourier transform on it to obtain the spectrum. So the principle is based on Michelson interferometer. We have a moving mirror, we have fixed mirror, and we have this is example with the laser source. So the moving mirror is moving like its name, and having this move, we create interference. So we obtain interferogram. So CTEL was built is Canadian instrument. It was built at Université Laval with collaboration of ABB in Canada, France, Hawaii telescope. Uh, its main characteristics are very interesting because, oops, yeah, one of the most important characteristics of CTEL is the large field of view. It's 11 by 11 arc minutes, with really huge. Is the widest widest 3D spectrograph for now until now. Muse, I think it's 1 or 2 arc minutes. With CTEL, we have 11 by 11 arc minutes. The spectral range is covering the optical part from 350 nanometer to 950 nanometer. We use different filters depending on the scientific goals, and we have 2 detectors to have 100% of the light obtained by the telescope, and the spectral resolution is variable. So we can have power resolution starting by 1 to 20,000. And the spatial resolution is limited by the seeing of the site. And what is wonderful is with only one exposure with this one observation run with this instrument, which takes 2 or 3 hours, we can have more than 4 million spectra. 4 million pixel, image of 4 million pixel, and for each pixel we have a spectrum. So for the study that I will present today, I will use only three filters: SN1, SN2, and SN3. So as I said, for this kind of instrument, what we obtain is interferogram, and by applying a Fourier transform operation, we have the real spectra. So this is example of different interferogram. When we have a complete interferogram, we have very high resolution. We have complete observation, but sometimes because the weather and for technical constraints, we can't have the full observation for the requested time. So we can still have the spectra, but with lower resolution. This is example of different interferograms and the corresponding spectra for them. So I already described the schematic, and this is a list of different filters used with this instrument. The main filters that I use is SN1, allowing to have the oxygen 2 lines at 3727 Armstrong, and SN2, which have each beta and oxygen 3 lines at 5007 and 4959 Armstrong, and SN3 allowing us to have the strongest emission line each alpha, and nitrogen 2 and sulfur 2. So at the end of observation, we have 4 million pixel, and for each pixel, like we see here, we have a spectra. So 4 million spectra, and we can use that to study extended object like galaxies, emission nebula, nearby emission nebula. That means galactic emission nebula, or nearby galaxies, and we can have no non-resolved emission nebula in nearby galaxies. So galaxies, I don't have a lot of time. So galaxies, we already know that there are different classification of galaxies. The first one was provided by Hubble. After that, Duvacular updated this classification by giving more details, including the presence of the bar, of the rings, and also the shape of the arms. So we have spiral galaxies without bar. We have with weak bar, with strong bar. We have some irregular galaxies without a very particular specific shape, and we have the elliptical galaxies, mainly from old stars. And this is example of these galaxies. We have elliptical galaxies here, so we have all the population of stars. We have spiral galaxies, so galaxies with star formation activities. We can see the star formation regions. We can see the dust produced by that, and we can see a lot of events interacting in the galaxy. It's live in galaxy. And the last category is the irregular galaxies. So they are very young galaxies. We don't have a specific shape, but we have a lot of star formation, and also some supernova, etc. So to understand the galaxy formation and evolution, we need to understand nearby galaxies, because we can study these galaxies in detail. And yeah, so let's before starting with NGC 3344, we will see some examples of galaxies in this video. So the first example is NGC 1300. It's a wonderful spiral barrel galaxy. So the bar is really strong. We can see it. We have star formation in the arms, in the center, lot of dust. So it's a perfect example to study spiral barrel galaxies. And here we say another example of galaxies, but this time is age on galaxies. And this is the Sombrero, the famous Sombrero galaxy. We can see lot of dust in this galaxy, which is related to star formation activity too. So the last example we have face on galaxy. That's what astronomers prefer to study because we have access to all the content of the galaxy. We have access to all the emission nebula, the star formation regions, supernova remnants. We can see the dust. We can see everything, the different structure of the galaxy, the arms, the bar, the center. We can, even if we have enough spatial resolution, we can see the stars also. So I took something similar, and it was NGC 3344. So I this is HST image of this galaxy that I studied, and during my study using 3D spectroscopic analysis, I was lucky to discover for the first time a sample of supernova remnant. So this work was published in Moumen 2019. So I will talk about that. First, the story of this galaxy is amazing because basically I was studying star formation regions in this galaxy, but when I was analyzing data, I noticed that few tens of emission regions had high quantity of sulfur, uh, which means that this is a signature of shocks, which means the presence of supernova remnants. So why studying supernova remnants? Supernova remnants are very important to understand the star formation and also the physics of the interstellar medium. Most of the massive stars, they end of their life on supernova, and the remaining gas, we can observe it via through the supernova remnants. So we can study the inside of the galaxy, the star after the explosion, by studying supernova remnants. And we can study also the interaction of the shocks with the interstellar medium surrounding the star or the stars. In our galaxy, more than 294 supernova elements were discovered. There is a wonderful catalog developed by Green and also by another by Samar Harb in high energy. So there are two catalogs updating our discoveries of supernova elements in our galaxy. So only almost 300 supernova elements in our galaxy. What is the advantage of this kind of object is we can study them in detail because they are very close to us. But the problem is we have a lot of extinction when we try to observe in the galactic plan, and the emission of optical and X-ray emitting supernova remnants is very hard to observe. And also we have a lot of uncertainties related to the distance of these objects, which impact our knowledge of the size and luminosity of supernova remnants. So the solution is to study extragalactic supernova remnants. And for extragalactic astronomy, they were only 25 galaxies with the extragalactic supernova remnants, and it was very hard in the past to do this kind of science because to observe all the galaxy and look for supernova remnants which are hard to identify, it requested a lot of time using traditional spectrograph, because we have like slit or small field of view, and we don't have a lot of time when we request time in big telescopes. So how we can observe extragalactic supernova remnants? We can do that in different windows, spectral windows, in the X-ray, in the radio, in the optical, and also in the infrared. But today I will talk about the optical supernova remnants. We use two lines, the sulfur and the H alpha lines. We estimate the ratio of these lines. If it is higher than zero point 0.4, this is a signature of presence of shocks, and this is a signature of the presence of supernova remnants. And we can do confirmation in the optical by using different emission ratios that I will show in a few seconds. So this is the galaxy that I targeted. It is NGC 3344, located in the Minor Leo, I think, Minor constellation. The distance is 9.8, and some people put it at 6.9 megaparsec. It's a wonderful galaxy with arms, with a wonderful inner ring, lots of star formation activity. And we observed it with using CTEL that I presented a few minutes ago. Next time. Yeah, so this is CTEL at the CFHT. For the spatial resolution for this observation, it was about 1 arc second, which is good. And it takes only between 2.7 to 3.1, so almost 3 hours to have a data cube with 4 million spectra. So I used three filters. So for each filter, we have interesting emission line allowing us to have different physical and chemical characteristics. So after observation, we use data reduction code. So we have one, the name is orbs to reduce the data because this kind of data are not like dispersive spectrograph. We obtain interferogram that we have to apply Fourier transform to obtain the spectra. So we need like a dedicated data reduction tool to reduce this kind of data, which was done by orbs developed by Thomas Martin in Université Laval, and also line fitting, because one other main difference is the shape of the emission line, of the lines in general and in the emission lines in particular. So we have the shape is sync. So we don't have a Gaussian, we have a sync shape. So we have to fit sync for this type of spectra. So at the end, we have more than 4 million spectra that we can use to do our studies. Here I present an example of two objects. So at the right, we have each two region spectrum, the H alpha line, the nitrogen line at 6583 Armstrong, and the two sulfur lines. Compared to supernova remnant spectrum, we can see that for the sulfur lines are higher. So that's why the ratio between the sulfur and the H alpha is higher than zero point 0.4. So this is one characteristic to tell us that, hey, look, you are maybe observing a supernova remnant. So also what we can do using this kind of data, we can produce velocity maps. So we have here, we found velocity, systemic velocity at near of the center of 579, which is in agreement with the data published in the databases. And also using that, we can have a velocity map. So we have red shifted regions and blue shifted regions. So we have the rotation of galaxy around the center. And to go back to the supernova remnants, to identify them, we use the sulfur 2 by H alpha ratio. So if we look to this map, I removed all pixels having low signal to noise. So all pixels with a signal to noise below 3, they are removed, and we have only pixels with good signal to noise. So as we can see, we have lots of red regions. The red regions means that each alpha is higher, is dominated, and this is a signature of photoionization. The mechanism of ionization is the photoionization, so energy coming from stars, and that means they are H2 regions. They are star forming regions. But also we can see some dark regions, like here in blue, in green. So we have regions with high quantity of sulfur, and there are many of them. So we can see them. They are not majority, they are minority, but they are present. And this kind of data, 3D spectroscopic data, allow us to do this kind of science. So this is RGB image. So we have each alpha in red and the sulfur in green. And we can see here, for example, we have a zoom here. The supernova remnants appear green, so punctual sources, and the issue regions appear in orange or red ranges. This is a wonderful example. We have star formation regions, and we have supernova remnant close to them. So also, yeah, we have access to each pixel of the galaxy. We can analyze everything, and the supernova remnants are very strong emitter of sulfur. So here we have, for this region, we have example of emission in H alpha in the top and sulfur 2 in the bottom. And we can see for this candidate, supernova candidate, we have strong emission in the sulfur 2 and weak emission in the H alpha. And to know that we are observing really punctual sources, real objects, we did a profile, so a pseudo void profile, to to see the distribution of the pixels around these objects. So in this work, I presented automatic technique to identify and to confirm supernova remnants in nearby galaxies. So we start this is a decision tree. We start by looking at the S2 by H alpha ratio. If it's higher than zero point 0.4 and the signal to noise is higher than 3 for the N2 lines and H alpha, we go to do next validation. The next validation is the Sabadan plot. So this plot, this kind of plot, I will describe it in a few seconds. It's cata- um, categorize the object that we are observing. So it can tell us if we are observing H2 regions or supernova remnant or planetary nebula. If also it's confirmed that we have confirmation from Sabadan plots which use N2 and H alpha lines and S2, we go to the BBT diagrams, which use more spectral, more emission lines, so we have more constraints to confirm these regions. So doing that, I have created three categories: the confirmed supernova remnants. So they are objects with S2 by H alpha higher than zero point 0.4. They are in the good region, in the shock zones in the Sabadan plot, and they are also in the shock zones in the BPT diagrams. The probable SNRs, they satisfy the first two criteria but don't satisfy the last one. And the less likely supernova remnants, they satisfy only the first criteria, S2 by H alpha higher than zero point 0.4. So this is example of plot of Sabadan for all candidates of supernova remnants in NGC 3344. In red, we have the confirmed supernova remnants. In the green, the probable, and in the black, the less likely supernova remnants. In this Sabadan plot, uh, so scientists did like three categories. We have in this region in gray, we have the galactic supernova remnants. So all the galactic supernova remnants belong to this zone, and our supernova elements in our catalog, they are close to this region, and we don't have regions into each two regions, star forming regions, and we don't have planetary nebula detection. So for this first diagram, we use the H alpha by S2 and nitrogen by H alpha. For this diagram, we use the ratio between the two sulfur lines and H alpha by sulfur lines, and we can see the same behavior. So most of the supernova remnants are located on the gray zone dedicated to shock ionization. And here in the last diagram, we have the same behavior, but more dispersion because we have regions belonging to the H2 zone, into H2 zone in this diagram. So the BBT diagrams looks like this. They are three of them, but we don't have one line to create the third diagram. So we only have nitrogen 2, H alpha, oxygen 3, and H beta. And here we have oxygen 3, H beta, and sulfur H alpha. So we have access to these lines. We use them to do confirmation. And we can see here we have region of photoionization. So objects belonging to this region, the mechanism of ionization is photoionization, so stars, hot stars. And after this line, so we have a contribution of shocks. So we can see the black, so the less likely, and the green, the probable, most of them are located in the H2 zone, and the red regions are near of the shock zone. So the same behavior in the second diagram. So after that, I created a catalog of supernova remnant candidates uh, by giving the position of each candidate, the flux H alpha, the size, the distance from the center, and the ratio is 2 by H alpha. So what is wonderful with this kind of data is we have information for each pixel, like I said. So here an example, the plus is the spectrum by pixel, and the integrated spectrum of this region is the red star. So we have, if we don't have information pixel by pixel, we will have only this star, which is good. This is supernova remnants in the shock zone. And if we have stars, all the stars are located in the shock zone. The same behavior in the second BBT diagrams. But if we look at this example, we have a mix of red and green regions. We don't know what means. It is issue regions and a star that formed in this region exploded in supernova remnants, maybe. So if we look at the integrated spectra of this region, it's located here in the limit between photoionization zone and the shock zone. But if we look at the pixel by pixel, we can see that parts are located in the zone shocks and another part in the photonization. It's more evident in this second diagram. So we have some pixels, maybe the red one, in the photonization zone, and another part of pixels located in the shock zone, and the integrated spectrum is located here. So I think I only have 9 minutes, and I will introduce quickly one project. When I did this work, I finished it. Now I'm studying each two regions in the same galaxy, and I'm finishing my review to publish the second paper for this galaxy by studying the star formation regions. But the discovery of this population of supernova remnants inspired me to create the optical catalog of extragalactic supernova remnants. So that will be my postdoc project that I called OCSR. So OCSR aims to use data from CFHT, from CTEL, from the instrument CTEL, to create the largest catalog of supernova remnants in nearby galaxies. So the sample is based on data that observed with the signal program, and program is a program aiming to study star formation regions in more than 40 galaxies, nearby galaxies. So I will use this data to study supernova remnants in them. So I did this work for NGC 344. I already started working on that for two more galaxies, for NGC 4214 and 4449, which is an irregular one. Oops. And yeah, what is additional with this project OCSR? So the main data will be in the optical using CTEL and CFHT and signal data. And I will also use confirmation from X-rays data from Chandra Observatory. The data is already in the archive. I also observed I observed some galaxies using Subaru telescope using the iron 2 lines at 1.644 micron. I had a very beautiful data, wonderful data with very good spatial resolution comparable to the optical, and which is also corresponding to the X-ray Chandra data 0.5, 0.8, and zero point 0.8 arcsecond. And recently, last month, I was in VLA conference uh, in United States, and I was visiting the telescope and talking with people how I can use the VLAS data, the Very Large Array Sky Survey, if I can use this data to complement this project OCSR. Once I finish it, so epoch strategy, I mean identification by looking at the S2 by H alpha ratio, looking at the signal to noise because I have information for each pixel, looking at the size of the objects should be not very very wide, because supernova remnants will be smaller than 120 parsec. And looking also at the correlation of the objects, if we have a good correlation coefficient, that means we have like punctual sources because the objects in nearby galaxy. So confirmation using the systematic method that I described it in the paper, using the Sabadam plot and BBT diagrams. So this is some results for NGC 4214 and NGC 4449. All this kind, we can do that with standard long slit or the small field of view spectrograph. So we need a wide, large of view spectrograph with information for each pixel to be able to do this. So here, if we have a zoom in this part, we can see we have here a supernova remnants candidate that was identified in previous work. So I can see it also in this data. This is for another regions, for this region. So the ratio maybe, I'm not sure, but yeah, it needs to have more confirmation if it's higher than zero point 0.4. This is another example for NGC 4214. I looked at one previous work. They identified supernova remnant candidates, and they have only some spectra for some regions, not all of them. So I did like a cross correlation to see if I can find the same thing. So for these candidates, I can see it in my data, in OCSR data. So the this candidate is real. We can see it. We have a good spectrum for this supernova remnants. But here, for example, here I have LBZ67. We have correspondence, so I can't find this the supernova remnants. But at this place, I can't find anything. And also in this region, at this position, they found supernova remnants candidates, but I can't find anything. I have deep data, good spatial data, good resolution, but it looks like there is nothing. So maybe we have to study more these regions and to do double check to double check if these candidates are real. I did the same thing also for NGC 44, 49. This is a strong supernova remnant here. So we have confirmation using spectral information. So if we put these candidates in the BBT diagram, Sabada, they will be located at the zone shocks, the shocks zone. Yeah, so the same thing here. So I don't have strong H alpha emission, but I have a strong sulfur 2 emission. There are a lot of noise, for example, but we have strong emission from sulfur. Yeah. Same thing here, another example for NGC 4449. And this is data that I obtained from Subaru using MWAC's camera. It's a near infrared camera. So here we have iron 2 plus continuum. We have data from continuum. If we do a subtraction, we have nothing except iron 2 emitters. So if we look like we zoom in this region, so we can see that we have some one candidate here. So I did the same for, because I obtained data for the three galaxies. So I did the same. I didn't find a lot of iron 2 emitter, but I found some iron 2 emitters, because it's really hard to do this kind of observation in the near infrared. But I was able to identify some iron 2 emitter that are probably supernova remnant, because the iron 2, like the sulfur 2, they are signature of shocks. So doing this, all this kind like beautiful kind of works, I just presented one example is to what we can do using 3D spectroscopic data to study supernova remnants. I'm working on another paper for each two regions. Other colleagues already published wonderful works related to each two regions. Yeah, so we have wonderful outputs coming from this kind of data. And now the question again, are we alone? We have really lot of information coming from this kind of 3D spectrograph. And I find myself also with the same question, but now also with the 3D spectrograph installed in biggest telescopes in the Earth and also in the spatial telescope like James Webb Telescope. So now we have the same question that we have 100 years ago, but now in terms of planets. Is our planet, are we alone in this planet? So can we have a similar planet to the Earth? Can we have habitable planets? Can we have habitated planets? So can we have a life otherwhere? This is the next question that other people can answer. So take care and stay safe, and thank you for listening.
Thank you, Ismail. That was a wonderful talk. Of course, ending with a question gets us nicely to our nice next section, because of course we might have some questions for you as well. So thank you very much for covering, of course, light in 3D and the lovely details on the CFHT and sharing your wonderful astronomy. I'm going to use this moment to send you on over to Emma for questions from YouTube. And I'm not sure how many we'll be able to take, but let's pass you over to Emma and take it away, Emma.
Um, Great. Okay, we just have one question. I just wanted to know, you're doing this work that you're doing is with the Canada France Hawaii telescope. Would having or would you be able to do work or this same work with data from one of the space telescopes like Hubble or the James Webb telescope, or is it different?
Yeah, it will be absolutely technically possible, but realistically, maybe more difficulty. If we can cover all the nearby galaxy in short time, yes. But if it's take a lot of time, we know that spatial telescope, the time cost is very very high, very expensive, though it may be really challenged. We did that in the X-ray spectral window with the Chandra data. So we have lots of galaxies that were observed in the X-ray, but in the optical, uh, yeah, it will like maybe cost 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 of time, and it's very technically, yes, we can do that, but maybe it takes more time, and we don't have a lot of time in the spatial telescope. So technically yes, but realistically maybe it's difficult.
Cool. Thank you.
You're welcome.
We have another question. Do you ever use Galaxy Zoo in outreach, or is that a tool that you would recommend?
Can you repeat, please?
Do you ever use Galaxy Zoo in outreach, and is that
Oh,
a tool you would recommend?
yeah, no, I never used it. I already visited it and saw it. This is a good tool, a very good tool, but I never used it.
Cool. That's all of the questions we got tonight. Thank you so much.
You're very welcome.
Thank you once again, Ismail. I think we could probably stay here chatting quite a while, especially if I got to just talk to you about galaxies. But we do have to move on tonight, unfortunately. So I loved your stories, and I loved that you showed some of the spectra at the end of your talk. It was really nice to see. So with all of that and the questions being answered, I'm going to just say thank you once again for tonight, and hand over to our president of the Toronto Centre RASC, Tom Luton, to finish off the evening. So take it away, Tom.
And thank you very much. And thank you to our wonderful speaker. And good evening, everybody. Hope you're enjoying yourselves. Thank you for joining us on this first wintry night of the season. And let's get into our announcements. But before I get actually into the announcements, there's a milestone that I want to mention. It's an interesting milestone. Actually, interesting is not the right word, more depressing. So the McLaughlin Planetarium here in Toronto was for many years not only a very important astronomical facility, but was also the home of the Toronto Centre RASC. Why am I bringing this up? Well, the McLaughlin Planetarium opened on October 26th, 1968, and it closed for the final time on November 5th, 1995. That's a little over 27 years, or to be more precise, 9,872 days. Some of you in the audience who are fast at math are already seeing what's happened. Because 9,872 days after the McLaughlin Planetarium closed is today, November 16th, 2022. And so what this means is starting tomorrow, the McLaughlin Planetarium will have been a former planetarium for longer than it was an active one. And if that doesn't make you feel old, nothing will. So I thought that little piece of information needed to be brought to your attention. Anyway, let's move on to our announcements. So, as Elena said earlier, we've got two types of meetings here on YouTube. We've just had one of our speakers' nights. We've had our last speakers' night for the season, or for 2022, and our next meeting will be one of our RAN meetings, recreational astronomy nights. If you're watching us live, please say hello in the YouTube chat, enter some questions for presenters as others have done. If you are a new member, please introduce yourself, and you're coming to us from far, far away outside of the Southern Ontario area, please let us know where you're from. So our next recreational astronomy night is going to be on Wednesday, the 7th of December, 7:30 p.m., live at the Ontario Science Centre. Chris Vaughn will be talking about the sky this month. And then Alex Arjamand and Charles Young will be giving the presentation on the 2022 annual Algonquin adventure. As I said, live here on YouTube, immediately afterwards will be the 2022 annual meeting of the Toronto Centre of the RASC. So it will be a Zoom meeting that'll start immediately after the meeting, as I just said. The invitations have been sent out by email. If you have not received an invitation and are a member of good standing, please contact the national office to confirm your latest renewal status, and as well drop me a line at president@rascto.ca. The agenda, the last year's minutes, and the slate of council candidates for the election are currently on the website, and you must register for the Zoom meeting in order to attend no later than midnight on the 5th of December. As well, for anyone who'd like to join council, nominations are now being accepted. To be nominated, the member must be in good standing, and the nomination form requires the signature of two members also in good standing. Deadline for additional nominations is Wednesday, November 23rd at midnight. That's next Wednesday. Email everything to our secretary, Lucy, at secretary@rasto.ca. And as we've said a couple times already tonight, our next speaker's night, there is none in December. We'll be seeing you in January. And it is our intention going forward into the new year that we will be having live meetings at the Science Center each month in the Gemini East room. The location may change. These meetings will still be online. However, so hosts and presenters and audience members can join remotely. This means, of course, that bad weather we will switch to a purely online only, with no more canceled meetings. We are recommending the wearing of masks, but we are not going to be enforcing it. And for the time being, our speaker nights will remain completely online unless we have demand from the membership for in-person meetings. Coming up for our observing sessions, the next City Star Party is at Bayview Village Park, the first clear night of the week of November 28th to December 1st. The CAO, the snow has been flying, so at this point we can be fairly certain that the road is nicely blocked off. Um, However, access is still possible if you're willing to trudge in a little bit. Access to CIO facilities by members and families only in a modified communal fashion with a total site occupancy limited to 25 individuals. The upstairs washroom is for upstairs bookings only. Max occupancy for the upstairs bedrooms are 2 people from the same family per bedroom for a total of 6. Communal areas are limited to 3 people wearing masks. All CAO users can use both kitchens, the downstairs washroom while wearing masks. The full details are on the website. Please read everything before you make a booking. We're still trying to fill some spots on our job board. We are still looking for an education and public outreach chair, a light pollution committee chair, a volunteer committee chair, and a marketing committee chair, as well as committee members. Our AV committee, the folks who work so hard to put on these wonderful shows, are always looking for additional help. And the Education and Public Outreach Committee is also looking for online presenters, especially anyone who is a telescope camera operator who can assist with virtual star parties. A reminder that in order to volunteer, you first must be a member of the Toronto Centre. If you're interested, please contact myself at president@rascto.ca. If you've been watching and you're not a member, and all this stuff that we're talking about and we've been describing sounds really, really interesting, can I invite you to please join the RASC? You can sign up or renew online at secure.rasc.ca. As well, it's the holiday season and gift memberships are available. Contact the national office at mempub@rasc.ca. And with that, I'd like to wish you all a very pleasant evening. Thank you very much for joining us. Please follow us on all the forms of social media that we've got listed here. If you're watching us on YouTube, please like and subscribe, hit the notification bell for further updates. Be safe, keep looking up. Good night.